Hey everybody, it's Ripley. All right, we're going to go ahead and finish up this chapter. We're going to talk about the binomial. We're going to revisit that guy because something funky is going to happen. The binomial approx to the normal curve. Now, this may seem like way out in left field. It's like, wait, we just did all this cool stuff with the normal curve and sampling distributions and the central limit theorem, and we got this new formula for finding z for sample means, rather than just for individuals out of a population where we know what the shape of the distribution is. Boy, I just summed up about the whole semester, didn't I? And all of a sudden you throw in a binomial approximation of the normal. Well, let's just stop for a second. Let's revisit what binomial means. We know that n is the fixed number of trials. All right. We know that x is, what did we say? N is the fixed number of trials. X is the number of hits, right? Remember how that worked? P is equal to the probability of a hit, prob of a hit. You're writing terribly. And Q, which is 1 minus P, equals the probability, just because we can use the complement, probability of a miss or a not hit. Whoa, a miss. Oh, you're going to have to bear with me. A miss or the complement of a hit. All right? Right? So we know that the probability that X equals big O X, where big O X is just a number, we're not afraid, right, is just n choose big O X, P to the X, Q to the n minus X. Okay? Now, just a quick little refresher for those of you that, that may not remember that. Now, I'm going to show you something. I'm going to use an applet to show you something that's pretty cool. All right, so I'm going to escape out of here and we'll go look at this applet real quick. Okay. Now, n is the number of trials, right? It's the number it's the number of outcomes that we can possibly have, right? That makes sense? So remember, n was like, what did we talk about? Oh, we did this, the number of Big Macs that come out in n cars, or excuse me, in 10 cars. So it could be 1 Big Mac, it could be 0 Big Macs, 1 Big Macs, 2 Big Macs, etc., etc. Sorry guys, I'm a little distracted. There's some construction going on down here. So hey, yeah, let's do that. Let's talk about, what did we do? We did 10 cars. I think we did 10 cars. And we said the probability of a Big Mac was 0.7. And then what I'm going to do is I'm going to do something very much like a sampling distribution. Okay, I'm going to do this. I'm going to show you real quick. I'm going to do this 1,000 times. All right. So think of this as I watch cars go through a drive-through 10 at a time, and then I do that 1,000 different times. All right. And let's simulate this, and I'll show you what happens. All right. Now check it out. What does that look like to you? It almost looks normal, doesn't it? It almost looks perfectly normal. In fact, remember, the maximum number of cars that could get a Big Mac was 10. If I could just extend this guy a little bit further, it would probably look really close to normal. Now, let's make sure we read this correctly. Remember, I sampled 10 cars at a time, randomly, and then I watched this happen. I did that process 1,000 times. All right? None of the times, there were no times that of the 10 cars, nobody ordered a Big Mac. There were no times that only 1 out of the 10 cars ordered a Big Mac. There were 4 times that 2 of the cars out of the 10 ordered a Big Mac. There were 7 times there were 7 times when 3 out of the 10 cars only ordered ordered a Big Mac. Wow, it's a lot of numbers floating around, isn't it? 28 times when 4 out of the 10 cars ordered a Big Mac, etc., etc., etc. Notice you got a nice high spike right here, which is, we know that's got to happen, right? Remember, the mean is n times p. It's going to be right here in the middle of this thing. Now, watch this. Watch what happens if I change the probability of ordering a Big Mac from 70% to 50% or 0.5. Watch what happens. Ooh, yeah. Look at that. Isn't that cool? Now, if I simulate it, remember, these are random samples. So it's going to change, but they all look very normal. Now, what happens if n equals, say, 25? All right, now think about this. I'm now grabbing 25 cars at a time. Now, instead of 0.5, let's do 0.6, just for giggles, okay? And instead of 1,000, let's do 100. Watch what happens. Whoa, that looks strange, doesn't it, right? So remember, we've got 25 cars, and this is the grouping around the number of Big Macs that they order, okay? Instead of 100, let's do 1,000. Watch what increasing the number of times that you do this, think of it as sampling distribution, right? Does to, whoa, just like that. You got yourself a normal curve. Now, it's clearly not normal because a normal curve is a continuous function. Remember how we defined that sucker with that awful e to the negative x minus mu squared over 2 sigma squared? It was that awful formula. And these have discrete values. These have discrete values. It's not like our normal curves where we had continuous values, right? If we take the heights of women, they can have any value theoretically between 0, that's a small woman, and 900,000 feet tall. If that were true, I would be in trouble. All right? I have a very tall girlfriend, but she's not 900,000 feet. Okay? Etc. You see how this works? Look at the difference. This is on a continuum. The area under the curve is 1. This is not. However, if I add up all these values, remember when I did it before, what did I do? I did 10, and I did 0.7, and I did it 1,000 times. If I add all these values up, I get all 1,000. All right? I get all of the possible combinations that could have happened. Okay? So what we have is an approximation to the normal curve with this guy. Okay? Now, if we have an approximation to the normal curve, that's the second time I've done that, then what am I allowed to use? What sucks everything down to every normal curve, or excuse me, to the standard normal curve? We have a z-score, okay? And the z-score is, what is it? It's x minus mu over sigma. Now, this is where it gets a little bit crazy because we actually know that if we're looking at sample means, then it's x bar minus mu over sigma over root n. But because we're talking about the binomial approximation to the normal curve, what we're really talking about is this x right here is the same x is over here. Okay, now let me show you. We're not panicking. Hopefully you remember from when we talked about the binomial curve, excuse me, binomial curve, the binomial probability distribution, you remember that mu was equal to, remember how that worked? It was just NP. And sigma was equal to the square root of NP cubed. Remember how that played out? Now wait, if mu equals NP, and sigma equals NP cubed, we are so golden. That's the coolest part, right? So all I have to do is use this formula. Now, let's go back to, excuse me, let's go back to the Big Mac problem real quick. Before we get into the Big Mac problem, there is a set of assumptions that we have to meet before we do a binomial approximation to the normal. And it's kind of a biggie, and it seems arbitrary, but it's proven using all types of statistical methods. The assumptions, you're going to hear a lot of assumption. I still hear it. I'm getting a PhD and I'm dealing with statistical analysis, and you have to meet your assumptions. You have to meet your assumptions. And that starts becoming really important here in the next few chunks of information. The assumptions for binomial approximation using the normal curve, I'm just going to call it binomial approx if you guys don't mind, are really simple. We have to have NP being greater than or equal to 5 and NQ being greater than or equal to 5. If they're not, in other words, N has to be big enough and P and Q have to be big enough such that their products with N are greater than or equal to 5. Otherwise, all hell kind of breaks loose on our binomial approximation. All right. So I'm gonna hedge I'm gonna cheat a little bit on the Big Mac problem. Instead of n being 10, remember how that worked out? Instead of n being 10, I'm gonna let n be 100. So we're looking at 100 cars. We know that P, is equal to 0.7, and we know that Q is equal to 0.3. So hopefully you remember, if I were to draw this thing, if I were to draw a probability distribution, I know that NP is equal to 70. Whew, that one's met. I know that NQ is equal to 30. Okay, sweet. We're in good shape. I also know that that mu is equal to NP, so I know that's where the mean is, and I know that sigma is equal to the square root of NPQ. Remember that guy? That's this guy right up here. So this is equal to the square root of what? 100 times 0.7 times 0.3, which is the square root of 21, which is about halfway between 4 and 5. Okay? So if I were to do this, I mean, think about what that distribution would look like. We'd have a whole bunch of values that started at 0 and that ended at 100. Over here at 70, let's call this 70, we'd have this peak. This is where the mean was. Remember, this is a probability distribution. And then what I'd end up with is a whole bunch of stuff that went out and looked approximately normally distributed. So I could draw this like that. Now there's something to keep in mind that's very, very important here, and it's going to come into play here in just a minute. It's that the normal curve, this guy, is continuous. You can have any value from, let's see, if I'm on the standard normal curve, right? I can have any value theoretically between negative infinity and infinity, although those really big numbers are highly improbable. All right? Excuse me. So a binomial probability distribution has discrete values. In other words, the number of cars that can order a Big Mac can be 70, they can be 69, they can be 68, they can be 71, they can be 72, etc., etc. It's not possible for 71.3 of the cars to order a Big Mac. They either do or they don't. And that becomes really important when we use this. So watch this. Let me show you why we use the binomial approximation. All right, we've met the assumptions. Let me show you. You may say, well, Ripley, wait, we have the formula. Remember this guy back here? The formula is sitting right here. The probability that x equals the number of hits is this formula. But what if I ask you this? What if I ask you the probability that x is less than or equal to, say, 60? Well, think about that in the binomial context. That would be equal to the probability that none out of the 100 cars ordered 1, plus 1 out of the 100 cars ordered 1, plus 2 out of the 100 cars ordered 1, plus ... all the way up to the probability that 60 out of the 100 cars. We'd have to figure out 61 distinctly different probabilities, and that just doesn't work. All right? So I'm going to rewrite my stuff. I know that what was n equal to 100, P was 0.7, Q was 0.3. Let's see, mu was 70, and sigma was the square root of 21. All right, so let's think about this, because we're going to do something a little bit crazy here that might make you guys nervous. We're using the normal curve, the standard normal curve here. However, we have to remember that this actually corresponds to 70, and then somewhere over here corresponds to exactly 60. And what we're looking for is 60, 59, 58. We're using the normal curve to make our workload easier. All right? So instead of having to do it this way, we're going to use the same technique as we used for the normal curve. So we're not going to look for the probability that x is less than or equal to 60. We're going to look for the probability that z is less than or equal to some value. Now, how am I going to get this z? Well, traditionally z equals x minus mu over sigma. But since we're in the binomial context, we know that what it's going to be is, it's going to be x minus mu, which is np, divided by the square root of np. PQ. Now there's one little trick here that's going to drive some of you guys nuts, but we'll try to do a couple problems. Remember, binomial is discrete. It's a discrete variable. It's the number of people that ordered the Big Mac. And the normal is continuous. So it's impossible because exactly 60 doesn't have any width to it. There's no area for exactly 60. So what we do is we do something called a correction for continuity. So there's exactly 60. Let me change colors one more time. And over here is exactly badly drawn, is exactly 61. And all that we do is we correct for continuity by grabbing the value between 60 and 61, which clearly is going to be 60.5. All right? That's called a correction for continuity. If you don't understand what I mean by that, I'll do another problem for you here in just a sec. Okay? Pardon me. Okay, so let's go back here after we've done our correction for continuity, and let's figure out our z-score. It's going to be, let's see, 60.5 minus 70, which is the mean, right? It's right up there, divided by the square root of 21. Well, I'm going to pull out my handy-dandy calculator. What is that? Let's see, negative 9.5 divided by root 21. And if I pull out my calculator, I get negative 9. That's negative 9.5, isn't it? Negative 9.5 divided by, say, root 21, and I get negative 2.07. Negative 2.07. Now, so z equals negative 2.07. So what we're looking for is the probability that z is less than negative 2.07. Well, where do we go to find that? Well, you guys know where. I'm going to stumble over here, and I'm going to go to negative, I got positives up here, I've got negative 2.0, there, right there, let me scooch up here just a little bit, negative 2.07, I cruise over here, 2.07, and I get 0.0192. Hey, look at that. If I grab this, the probability of getting less than or equal to 60 cars out of the 100 is approximately, I'll use approximately equal, because remember this is an approximation, is 0.0192. So on average, you can expect about 192 out of 10,000 of those cars to order less than or equal to 60 Big Macs. That's pretty cool, huh? Let's do one more, because I know that correction for continuity is just a little bit crazy. Let me change my pen. Let's do orange. I want to find the probability that, let's see, it's 70. I want to find the probability that the number of cars that order a Big Mac is greater than, let's say, 90. All right, now think about this for a sec. So I have no idea where 90 is. I can't do those types of things in my head. But let's say that 90 is right there. Now I'm looking at greater than 90. So remember, this is going to end up being the probability that z is greater than some value, and we'll find that value here in just a sec. But if I'm greater than 90, I don't include 90, but I want to make sure that I include 91. So what I do is I correct for continuity, and I grab the value in between, which is 90.5. It just grabs that value directly in between, so that, notice when I shade in, I definitely pass through 91. I also pass, turn this thing into black, I definitely also pass through 92 and 93 and 94 and 95 and 96 and 97, etc., etc. So let's figure this thing out. I know that z is going to be equal to 90.5, excuse me, minus 70 divided by the square root of 21. Oh wow, this is going to be crazy, isn't it? That's 20.5 divided by root 21. This is equal to 20.5 divided by root 21 is equal to 4.47 standard deviations away from the mean. Think about that. What's the probability that greater than 90 people out of the 100 are going to order Big Macs, given that the probability that any single vehicle orders a Big Mac is 0.7? They've done market research on it. What's this equal to? It's approximately equal to 0. In fact, if I go stumble over here to my z value, look at this. It doesn't even go as high as 4.47, whatever it was. It only goes as high as 3.49. That's something else right there. All right? This binomial approximation to the normal gives us an extremely powerful tool in trying to figure out a whole bunch of probabilities at once. Because remember, bear in mind, if I have to do this by hand, I have to do the probability of exactly 91, remember I'm greater than 90, plus the probability of exactly 92, plus the probability of exactly 93, plus plus the probability of all 100. So that right there is your binomial approximation to the normal. I hope you enjoyed, and that right there is the end of the chapter as well.